Hi, guys. I don't know if everyone who wants to be here is here. Maybe. Hi. Well, you were just there. Hi. Uh, don't know. Okay. Well, okay, so we start and then. Okay, so let's try coding lemma today, yeah? If I had to like single out a single theorem in descriptive set theory, which is important, it's this one. Which is funny because everybody always says that the recursion theorem is a triviality, and it's recursion theorem that proves this. So, I mean, coding lemma is highly non-trivial. So, anyway. So, okay, well, let's start. I'm not sure. We should wait longer. Spartak usually comes, but he's not here. All right, so the cheap version first, right? Because the cheap version doesn't actually use code. Recursion theorem. So the cheap version is following assume AT. Right? Suppose there is a surjection F from the reals onto alpha, right? Then there is H from the reals into the power set of alpha, H, a surjection. Okay. Okay, so the proof is going to be by induction, of course. and then at the end we'll be done, right? Okay, so in that the successor case is easy. So homework. If that exists, age. There is okay. Right, so I don't need to prove the successor case stage limit, right? So suppose we have xi less than beta and beta a limit, right? You want to define h beta. Okay, all right, so what's going to happen? We're going to take a subset of beta, play a game, and prove that the winning strategy for either players uniquely determines the set, right? So idea, assign to each a assign GA to play a game such that winning strategy for GA uniquely determines A. Okay, and then that will be your map. Each take any strategy. Let's take the winning strategy of GA and map it to A. Right, so you have it. Okay, so what is the game? Well, the game is actually not too hard. You have A, and so you can look at game is like this. So one is trying to code. One is so this is the idea. For this game. One is calling A intersection xi0, and two wants to code A intersection xi1 for xi1 greater than xi0. So one is trying to code some portion, initial segment of A, and two is trying to code further. Why is this going to be good? So remember, our goal is to show that the strategy is going to uniquely determine A. Okay, if it was once strategy, then let's see if it was one strategy that one. Okay, let me tell you the game. Might be more clear there. Yeah, if it was one, say one is winning, yeah, and suppose there were two games like these that one was winning with the same strategy, then take A and B, which are different. So say one is winning. I want to show that if one wins, then my first idea works. Yeah. So let sigma be a winning strategy for one. I haven't told you the game, but imagine you had a game like this, where one is coding that much, and two wants to code further, and one is winning. Say, okay, we want to see that sigma that A is the only subset of beta for which one wins GB with sigma. So the sigma couldn't work for some other strategy. Well, simply because imagine you had some other beta or some other B, fix, suppose not, right? Let B be such that sigma is also winning strategy for one in GB. Okay, then, but they're different sets, right? So let psi be saying the symmetric difference of AB, and then pick, and then let's now to code. I haven't told you what that coding means. To code A intersection psi plus 1. Right? If A is coding this far now, if 2 is coding this far, 1 hasn't lost, so 1 has to code further, right? But then psi cannot be both in A and B, because if 1 is a winning strategy, right? So then if psi prime is 1's response, then A1 is calling both A intersection psi prime and B intersection psi prime. But that can't be, because one is coding only one of them. They're different things. One cannot code both of them. Okay, so we need to find a proper way of saying one is coding something. And we do have that, right? I can let one play the code for this set. What is the code for that set? I already have a surjection from reals onto that, right? And so that's what I will let for one play. Okay, so 1 and 2 play. So 1. So what do I have? I have F. My setup was F onto alpha, and I have this H size, right? So we have F that goes onto, and I have H psi that is going onto psi less than beta, right? This is the information I have. Now fix A subset of beta, GA. Now 1 and 2 are going to play x0, y0, x1, y1, and etc. Right? Now one will lose if F is telling me what ordinal to look at, right? So if if H F x0 then I have x is x0, x1, and y is y0, y1. So think of the even digits and odd digits, right? Say x0 is even digits of x, and etc. Right? We have given a real, you can split it into 2. Okay, so I'm looking at the first portion of that real. I'm looking at the corresponding function, and I'm asking if that is what is equal to, right, A intersection F x, unless. Okay, so this is one's condition. and 2 loses unless f y 0 is bigger than f of x 0 and h f of y 0 y1 is bigger than a codes and this is for 2. So what happens? Remember, the idea was that 1 is going to code an initial segment of A. Okay, how is going to do it? Well, my f is coding ordinals less than alpha. I can let 1 play a real and look at the value of that real. So that's an ordinal. And then I have another sequence of functions that are coding power sets of those ordinals below, right? So I can put the second portion of my x1's play and ask if they match, right? So this is what I meant 1 is coding an initial segment of A. When we're saying 1 is coding these, that's what we mean. That's how you can say that using reals. And 2 loses unless 2 codes further, right? Is this clear? I guess Brian usually says something. Brian, is this clear?
Is it obvious that you can't have both lose or both win or something? Because they're playing like sort of separate things, I guess. Don't really, it's not important, right? Because I'm going to prove that if 1 wins, then there is only 1 A. If 2 wins, there is only 1 A.
I think what James means is that, right, that what happens if both of them fail to code A, right?
Well, if one loses unless if 1 didn't satisfy this equation, then lost. And if 1 satisfied that condition, then 2 had. So first look, oh, I see what you mean. Well, if 1 satisfied this condition, then 2 has to satisfy that condition, right?
Okay, so the winning condition for 1 is like 1 loses unless 1 meets that condition, then 2 wins if 1 loses, or they win if 1 satisfied that condition, but they coded A even further than player 1 managed to, right?
Yes. Yeah. So if 1 didn't satisfy this condition, then she just loses. If it did, then 2 wins if 2 satisfies this condition, right? So let's see. 1 loses unless if 1 doesn't lose, then 2 loses unless this. Right. Now it's clear, yeah. You ended up playing this. If 1 didn't satisfy that condition, then she lost. If she did satisfy it, then you look at 2's board, and if 2 ended up above 1, then 2 wins. If 2 does not satisfy this condition, then 1 wins.
Okay, so if A is like a bounded subset of zeta, right? Then you can have A intersect fx0 and A intersect fy0 should be the same thing, right?
Yeah, so then one would win by playing the code for A.
Well, no, because Y could just 1 could play a code for A, but then 2 could just play also the code for A, but play a bigger ordinal.
Then 2 wins.
Okay, so for bounded subsets, 2 always wins, right?
Yeah.
But the only interesting case
2 would just play above. But we already enumerated them, so the interesting case is the unbounded subsets.
Okay.
Right, the bounded subsets are enumerated already by one of these functions. Yeah.
Okay. So we understood what the game is now, I guess.
Wait, we have, so I get when you have a surjection from the reals, you can, like, if you had a countable sequence of reals, I would know how to code it, right? So you like code the bounded sequence, the bounded ones via a real, and then you code like the unbounded ones. Is that going to be?
No, I'm doing the induction on alpha, yeah. So at the end, I will have H alpha, which will be a function like this.
Well, so what we're doing, we're coding the bounded subsets of H alpha, right? But each of those can be coded by,
I'm not
I
gonna
guess,
put, Brian, we're not putting these functions together. We're just defining them as we go. Now, my goal is to define H beta.
okay, so we have those functions, we've enumerated them, and we're still trying to define the
By
function that
induction, we build,
enumerates.
yeah, we're building these functions by induction, and the induction goes up to alpha. So at the end, I want to build my final function H alpha, right?
Okay,
Yeah, so we're not putting these functions together, otherwise it wouldn't work like you're saying. I mean, or you will have to play a cycle. It would work if you had the coding lemma.
well, I mean, in the successor case, I am essentially just putting the functions together, but in the successor case, I just have like two functions to put together, so it's fine, right?
Yeah. And the successor case is triggered. So we're doing this. Okay, so now what I want to prove is that if one wins, case one, one has a winning strategy. I guess the claim is that whoever has the winning strategy, there's only one A that for which that's a winning strategy. So maybe I write it like that, and then it could be. The lemma is lemma. Suppose sigma is a winning strategy for either of the players. A is the unique subset of beta for which sigma is a winning strategy for that player. Well, I guess I don't have to say that. Because a strategy for a player, you can distinguish them, right? Strategy for one tells you what to do initially. Strategy for two doesn't tell you what to do initially. The response. So this is probably good. So if I hand you sigma, you will determine if it's for strategy for one or strategy for two. Okay. So let's do case one. Sigma is a winning strategy for one. Okay, suppose B subset of beta is such that B is not equal to A, and sigma is a winning strategy for one in GP, right? So now let Xi be in the symmetric difference. Yes. And let Y1 be such that, let's say, F HY1 H Xi plus 1, right? Is equal to A intersection Xi plus 1, right? Now let Y0 be such that F Y0 is psi plus 1. Right? Remember, my F was coding ordinal less than alpha. The H sequence was coding the power set of the ordinal that's here. Right? Now let 2 play this real. Now let 2 play y equals y0, y1. Right? So what happens? Let x be sigma star y. So one's response. Now what happens? Because 1 wins GA, we have that's because 1 wins GA, we have, maybe I'm making a mistake here. So 1 wins GA, I have what? I have that, this is the winning condition. So 1 loses unless this, right? So this must happen, and 2 cannot be above. So this must happen. I have that H f of x0 applied to x1 must be A intersection f of x0 and has to be longer, right? And f of x0 has to be longer than f of y0, which was psi plus 1, right? F of y0 was psi plus 1. So contains psi. May not contain psi. Let's see. But now I cannot have right. So now 1 wins. Now 1 also wins. So HFX0, FX1 is what is bigger than psi plus 1. No, I have it there. Yeah, so I don't have it. Now we look what happens in GB. Now because 1 wins GB, we must have that. Right, so let's go look at the conditions again. If 1 didn't satisfy this condition, 1 has to lose. So 1 is not losing, so it means has to satisfy that condition. Right? It's the same x0 and x1. I have to have x0 x1 is equal to b intersection. What?
Because I think that's the point where Brian's doubt now is actually relevant, right? Because so you say if 1 wins, then the first condition is not satisfied. If I understood what you said before correctly,
let's see, 1 loses unless this happens. If it didn't happen, then 1 loses. Right?
But yeah, but you say this, but yes, but you now say but 1 wins. So,
yeah, so this must
if
happen.
No, but if I understand, if 1 wins, right, it might happen that this doesn't happen, but the next point doesn't happen. The next.
No, it says no.
If the first
1 loses. If this didn't happen, 1 lost. Right?
Okay, and then
this is what it's saying. 1 loses unless. So this must happen.
No, but okay, Grigor. So like call this condition box 1, call the second box 2.
Okay, so let's see. One loses unless one, right? So if one
So you
one
say-
wins, then one has to happen. Because if
Yeah, so
one failed, one loses.
So you say this, if not one, then one. Then one doesn't win, right? If one wins, then one. That's what you say.
If one wins, one has to happen. Otherwise, one
Yes.
loses.
Okay. And what?
One wins if only one holds and two fails. Yeah. So one, I guess what James is saying is that one wins if and only if one holds and two fails. Right. So if one is winning, then this condition has to happen, or it's losing. Then we move to the second, right?
Yeah, I
Okay.
needed exactly what James wrote, right?
Okay.
Wasn't.
So now we have. So I have to have this condition, but that's a contradiction, right? So this is because f of 0 is greater than or equal to psi plus 1. We now have that d intersection psi plus 1 because of that is equal to a intersection. Okay, all right. So let's go to the case 2, which is very similar. Two rings. So suppose sigma is a winning strategy. Oh, I already had a winning strategy. Yeah. So case 2 is sigma is a right. Okay, so if one maintains, so what's the point now? If one maintains that condition, then 2 has to maintain this condition, right? So if one maintains box 1, then 2 has to maintain box 2. Okay. All right, so let's see. So now want to see that sigma is the only wins GA, right? I suppose the subset of beta is such that sigma is a winning strategy for 2 in GB. Now we can play the same trick, right? Fix psi in asymmetric difference B, and now code it again. But now let one play that, right? So let x1 h psi plus 1 x1 be a intersection psi plus 1 and x1 be, let me see, am I making sense now? Well, no. No. Okay, so my lemma, I should have stick with my notes.
If 2 wins, it's not that this is not true. It's the only A is the only subset for which 1 wins according exactly that way. Okay, so so if 2 wins, then A. Now the claim is that. Okay, I have to correct this. A is the unique subset of beta, such that for every X unique subset X of let's call it B, unique subset B of beta, such that for every real if y equals sigma star x, right? So if I let one play x and this is my response, and a b intersection f of x, what was I using? X 0 is h, sorry, yeah, h f of x0 x1, right? So if this, then so if this, then f of y0 is bigger than f of x0, and b intersection f of y0 is h. F of y0, y1. So it's not that the sigma is still uniquely determined, but the lemma is not completely correct. My lemma was saying is the unique one for which sigma is a winning strategy, but my notes don't say that. So let me say the lemma a little bit differently. Yeah, suppose sigma is a winning strategy for either of the players. Then A is uniquely determined by sigma. Then A is definable from sigma without parameters. Right? So here, what is the formula that defines A? Well, it's the unique subset for which sigma is a winning strategy for it. And in this case, that's the formula that defines it. Right? So this is my formula that defines A. And you could see it's the same thing, right? So suppose, so this is my formula phi A, phi B. Suppose B is not equal to A, and phi B and phi A hold. Right? And now I want to do what? I want to, so let psi be a symmetric difference. Peak x0 such that f of x0 is psi plus 1, and peak x1 such that h psi plus 1 of x1 is A intersection psi plus 1, right? Now I have what? So now we have what? Now we have well, we now have y this is true for A, right? So I need to have fy0. What is happening? Something is wrong. This x0 does not guarantee, does not code B, right? Maybe I should let the one play the other thing too. Why is this happening like that? Why is sigma star x? Sorry. We need to pick the least psi such that they are equal and then play that. Yes, sorry. This. Suppose both of them hold and let psi be least such that the intersection psi is a intersection psi, and now play psi plus 1, right? So basically it's the smallest element of the symmetric difference. Now let x0 be such that f of x0 is xi, and xi1.
You mean inequality in the, if you
No,
say
yeah,
like psi b,
Actually,
like
cool.
no, above like psi b the least such that big intersection psi is,
Yes.
because that
So,
looks like, I mean it's 0, right? You mean the greatest?
No, the minimum inside minimum. Yeah, you're right. Psi b minimum in the symmetric. So the soup, soup of the xi's with that property. So then the intersection xi is a intersection xi, right? Take the least one as the largest, the soup of the ordinal such that they agree up to their ordinal. So let x0 be such that f of x0 is, yeah, you're right. So you were right. And x1 be, let x0 be such that f of x0 and x1 be such that h f of x 0 x1 is whatever this set is, C, right? Let y be sigma response. Now I have this condition for both, right? We now have
Did you go back one slide?
yeah, I have both this condition for B and this condition for A. Can I go? Okay. So now we now have B intersection f of x0 is equal to h f of x0 x1, which implies, because f phi b is true, which implies this, right? So it implies that f y0 must be strictly bigger than f of x0. And so why does this imply that? Because sigma is winning strategy for 2. Sigma is a winning strategy for 2. Fy0 is bigger than fx0, and the intersection f of y0 is equal to h f y1 y0. No, y0 y1. And I also have that A intersection f of x0 is equal to h of f of x0 applied to x1. And for the same reason, that implies this. A intersection f of y0 is equal to h of f of y0 applied to y1. Yes, so that means, but f of y0 is bigger. So f of y0 is at least psi plus 1. And if I look at now these, what they're saying here, the left sides, the right sides are equal, so these sides have to be equal. The intersection psi plus 1 is equal to A intersection psi plus 1. And that's a contradiction. Right? So I guess my original lemma was correct. Well, what I said, my current version is also correct. This version is correct. A is definable from sigma without parameters, but it's the unique A is the unique set for which sigma is a winning strategy. Bartek, did I make sense?
I mean, the presentation was slightly confusing, but I think roughly. I mean, yeah,
Okay,
it's something,
well,
something I'll be able to follow, right? I mean,
so let's try again. So sigma is a winning strategy for 2. I want to show that A is the unique subset B of beta such that this formula is true. So if I'm playing a real and Y is the response, right? So if I code it this much, then 2 codes longer, codes a lot larger and longer, right? So if 1 satisfies this condition, 2 will have to satisfy this condition, right? Okay, so now take two sets, B and A, and suppose they both satisfy this formula. Take psi, which is in the smallest thing in the symmetric difference, which means up to psi they are equal, B and A. Okay, and so now I want to make sure that I code that set. This is the set. I want that to be C, right? So now I'm going to pick my x0 such that it's psi. Okay, and my h of x0 such that it's giving me C. x1 in a way that it's giving me C. So remember, HFX0 enumerates all subsets of Xi. In particular, it's enumerating C. Fine, and let Y be the response. I have this condition is satisfied because I'm coding exactly f of Xi, Xi0, X0 is Xi, and I'm coding exactly B intersection Xi. So this condition is satisfied, which means this condition should be satisfied. Right? And Fy0 is bigger than Fx0, which means whatever this thing is, HFy0, y1, whatever that is, should be B up to longer ordinal. But the same condition also holds for A. So whatever this thing is, should be A up to longer ordinal. Therefore, they agree up to Xi plus 1. But they weren't agreeing. Xi was the minimum in the symmetric. So Xi belongs either to B or to A. Yeah. So this cannot happen. Okay, that's the coding lemma. There's a interesting corollary, yeah. If basically theta is an accept, so theta equals geometry, and set theta equals the soup of alpha such that there exists f from the reals onto alpha, then theta is inaccessible. Meaning inaccessible in what sense? If some set has size less than some set has size the reals, then its power set is also size reals, so it's not size theta, right? i.e., for every alpha less than theta, there is. Remember, we don't have choice, so these concepts are a little bit weird. So for every alpha less than theta, there is no h theta onto. Right? And it's obvious. If there was such a, right, what would be the proof? Suppose h is a function, right, with alpha less than theta. So alpha is less than theta, that means fix. I can surject reals, so I can fix, in fact, onto the power set of alpha. Then compose, yeah. This is onto. That's a contradiction. Because theta was supposed to be this. Okay, this theta plays an extremely important role. In fact, there are no interesting theorems about anything that's bigger than theta. So that's a phenomenon, and it's basically no one has ever been able to do something. Well, now there are some new models of determinacy that are showing up where interesting stuff happens. But because of this theorem, and it's natural to expect that, right? I mean, what is determinacy? Determinacy is something about sets of reals, that it's saying that sets of reals are determined. The games associated to sets of reals are determined. So it's something about reals, sets of reals. And theta is the least place such that sets of reals cannot reach, right? It's inaccessible to sets of reals. And so it's natural that you shouldn't be able to say anything about theta. And that has been, yeah?
If you consider determinacy for games on, say, arbitrary set, right? This could make sense, right? Not necessarily.
Yeah, but they're not. I mean, yeah, maybe I should have said this. So here's it. assume AD, then the following game is not determined. You have to be careful exactly what you say. It's extremely difficult to come up with some other notion of determinacy. So here is the game. You have 1 and 2. 1 is playing just a single ordinal, and 2 is playing and 2 wins. So 1 is playing ordinal less than omega 1, right? 2 wins if X codes off. In terms of this coding that we had before. So let's see. Proof. Suppose 1 wins, right? But 1's winning strategy is just an ordinal, yeah? It's just telling you 1 ordinal, right? Let sigma be the strategy. So 1's move. So sigma is really just an ordinal. Is some ordinal less than omega 1, say alpha, right? And then that 1 doesn't do anything else. 1 just played alpha and that's it. Well, then pick, so pick X that codes alpha, right? And let 2 play it. Then X defeats sigma, right? If I let 2 play this X, 2 wins. Okay, so suppose 2 wins. That's a contradiction, right? So suppose 2 wins. Let sigma be a strategy for 2. And now we look at the sequences, responses, 2's responses to countable ordinals. Consider sigma alpha, alpha less than omega 1, which are 2's responses, right? Call it X alpha, alpha less than omega 1. So this is a subset of reals. If alpha is not equal to beta, then X alpha is not equal to X beta. If alpha is not equal to beta, then 2 is winning. X alpha codes alpha, X beta codes beta. So if alpha is not equal to beta, they cannot be the same. Okay, but AD implies, or their property, right? No omega 1 sequence of reals. Okay, so we talked about this is 20 minutes, and the other one, the other coding lemma is more confusing. So why don't I just go on lecture a little bit about this because it came up. Okay. So you could do. I mean, it's a big theme in by big. The community of people who study these kind of things was really big before, but now it's really not that big. Mostly because the problems are really hard. It's a really hard question. And it's a vague question. What sort of games are determined? Let's see. So you could do ADR. For example, ADR. What is ADR? Here you play reals, right? So A is a subset of omega. GA is 1 and 2 play X0, X1, x2, x3, and etc. So xi's are reals, and one wins if and only if the sequence. So it depends how you look at it. The sequence belongs to A. So ADR is consistent. This can hold. So there's a theorem of Wooden. Assume, well, I will state as a consistency result. AD, so let's say AD is consistent relative to omega with cardinals, and D ADR is consistent relative to omega wooden cardinals. A little bit different on this. So there is lambda limit of Woodens. These are large cardinal notions, which if you don't know, then think of some natural concept that's set to your study. There is lambda limit of Woodens and less than lambda strings. Right? There is also other things, like you could say long games. So let's see, games of length omega square. So 1 and 2 play integers now. And 0, m0, and 1. And then they start again, yeah? So it's like 2 rounds. Oh, omega square would mean omega times, so it's I guess omega rounds. Right, then you play, after that round, so omega rounds of this. Basically, omega rounds of the usual game, right? So the play, right? You play m0, m0, etc. You make your first real, then again you play and 1 0 and 1 0, etc. You play that. That's your second real. I mean, you could have just played 2 rounds, but I wanted to mention omega squared because, and then you ask some question, right? Because Blas showed one direction is natural, right? I mean, if all these games are determined, then obviously ADR would be okay, right? So determinacy of math omega square games on integers is equivalent to determinacy, is equivalent to ADR. So all these games are determined if only if ADR, which is natural. You could, in the ADR, you're playing reals. Well, it could be that let the first, I mean, there's something to think about, but it's kind of natural, right? Because it's not in the ADR, one's first move is the real that one wants. But if you run it like this, then it's not the real that one wants. Your 2 is contributing to that real. Yeah. So there's something to think about. It's not a trivial argument. Yeah. But you can, I mean, once you realize that these games are determined, why stop? Right? Okay, but obviously you're not going to win any on length omega 1 game. There could be, right? Because how are you going to code with AD? You cannot do it, because if you let the game run omega 1 steps, you will produce omega 1 many reals. so you cannot have AD plus all length omega 1 games are determined, but some portions of it are fine. So for example, you could do the following. Length omega 1 games. So this is in quotation marks. You could let's say let phi be a formula. And so now we could play one and 2 play, right? And let's say they're playing reals. Doesn't matter what. So xi is a real. Now, when does the game stop? I cannot let the game, if I'm assuming AD, I cannot let the game run to actual omega 1. So I have to say the game stops. So when does the game stop? Stop condition. Right, so I mean you're playing x alpha plus 1, etc. So let 1 play the limit stages. That's not a big deal. So when does the game stop? The game stops. Let sigma beta be the set of x alpha less than beta. So you could, for example, say if beta is equal to omega 1 of L of sigma. Right, so if you look at that, and somehow beta is the omega 1 of that model, then stop. Okay, if these games are determined. Oh, and then what's the winning condition? So 1 wins if and only if you could say, oh, you could even ask a question about the entire sequence. L of the sequence I less than beta satisfies phi maybe I prove to you that all ordinal games can be determined. Let's see. I think that shows all ordinal games can be determined. You could say, can all OD games on reals be determined? Here's something that's not known. Let's see. Oh, this is due to Niemann. He has a book called Determinacy of Long Games. Which, yeah. Okay, so there's OD determinacy, which stands for any ordinal definable game on reals. By the way, I should say that he also, I mean, Niemann found lots of different versions of games where actually the play runs to omega 1. And then you ask then you have to be careful what to ask, because if you ask something crazy, it will definitely not be determined. But he had, which I don't remember on the top of my head, he had some nice condition that had to do with stationary sets, stationary subsets of omega 1. And he proved that some version of that game, a large collection of those games are determined. OD determinacy is just saying every game every ordinal definable game on R is determined. It's consistent. So of arbitrary length, right? I think this is consistent. I think wouldn't show that this is consistent. This is OD determinacy is consistent. Too large, relative to large kernels. But what's open is if some large kernel actually implies it. So game on reals means that the players are playing real numbers. Yeah. Does some large kernel imply OD determinacy? I'm trying to remember what Kekris-Martin argument actually gives you. I think, let's see. So I think there's a theorem of, let me formulate it like this and then see if it's a cute idea. Kekris-Holloway probably. I think they proved that for con of X, L of X satisfies all OD games on integers of length omega are determined. So for con of X, meaning for Turing con of X, if you look at L of X, then all OD games on integers of length omega. So you're playing omega times are determined. I could try to.
Under what assumptions?
Oh, I'm assuming AD. Or you can just assume delta 1 to determinacy actually. Proof? Yeah, this. I mean, this is shocking. If you get some used to what it's actually saying, it's kind of strange. So I don't know. Should I prove? I try to remember the proof. The proof is something like. So suppose not, right? So for con of X, there is an OD game which, because remember, con filter is an ultra filter, Martin's measure, yeah. Every set of degrees contains a con or is disjoint from a con. That was Martin's theorem. So if the theorem is false, that means, in fact, that there is a con of X for which L of X thinks there is an OD game on integers of length omega which is not determined, right? So if I say suppose not, then what I get is that then for con of X, L of X thinks there is an OD. OD means ordinal definable. OD game on integers of length omega, which is not determined. Right, so for con of X, L of X is going to think that in fact there is an OD game, which is okay. OD game means that the game itself is definable from a sequence of ordinals, right? Which I can minimize. Finite sequence of ordinals, they are lexicographically well ordered. So for each X, I have some finite sequence of ordinals, right? Now let be such that Sx is all less than omega, and in L of x, so A and B in L of x, there is a game definable from Sx that on omega that's not determined, and C Sx is minimal. Right, so minimize this parameter. Now we have a definable game. Oh, and notice that Sx does not depend on it depends on the degree, right? So notice that if x has the same Turing degree as y, then Sx is Sy. Okay, so what are we going to do now? We're just going to play. Now consider following game. So 1 and 2 play x integers, right? So 1 and 2 play I don't remember if they play. I guess we could just let, okay, let's just let x, so 1 plays x equals x0, x1, and 2 plays y equals y0, y1. So this is 1's play, this is 2's, okay. And now you want to say, so 1 wins. If a L of x0, y0.
So are they playing n's, m's, or y's, or xy? It's a type, right?
This is they're playing 2 reals.
Oh, okay.
This is in
You're
R2.
producing first. Okay.
See, I don't quite remember. I think this is going to satisfy, so, but this doesn't make much sense. The winning condition has something to do that now you want to say x1 and y1 is a run in this non-determined game relative to this play. So satisfies that x1, y1 is a run of the non-determined OD game. That was definable from this pair. Definable OD game that is definable from the pair x0, y0, and that finite sequence of ordinals. And B, 1 wins the run. This one, right? So the first portion of the real is going to code the L, and then you say, well, the rest is just a run of the game that you would have played in there in this model L x0, y0, and 1 wins the entire run of the game. If 1 wins the game that they're playing in that restricted universe, right? And now you let the sigma be the strategy, and you want to argue that sigma is actually a winning strategy Okay, so I'm gonna blah a lot if I try to do the proof. I think it's something like this. Maybe I can check it. This was not supposed to be something I was gonna say to you. But I think this is how it's a good approximation. I'm feeling a little bit worried about splitting these two. I think they should somehow play the same real and then something like this. So you end up showing that if you have a winning strategy for this game, then any real that codes the strategy, yeah, that's the thing, yeah. So let's see, if suppose one wins this. Suppose one wins this game, right? So I'm gonna play, so let sigma be the strategy, be the winning strategy for one, a strategy, should not the winning strategy. And yeah, so I want to claim now that let Z be above sigma, then LZ models will be determined that one wins that bet game given by SZ, that finite sequence. Okay, so why is this good? Why is there any hope? There is a hope because sigma is there, right? Notice sigma is in L of Z, right? And so if I let one play, now this is like the Martin's measure trick, right? So now let's have a run of this game. So let's say this game is G star, right? Now in let one play according to sigma star in G star, where sigma star records x1, y1. Look, sigma is going to tell me this. It's a winning strategy for one, so it's telling me two reals. I want you to play this one, x1, right? And what is going to be, no, one records, oops, x1, y1, but I want you to play as two by playing z as well. So x is going to be sigma responded to z zy, right? You see what I mean? Okay, we don't have much time, but what I'm trying to say is that two is playing something in that bet game, right? Pair that bet game with z and let that be two's play in the other game, in this game, right? So you're playing this z and you're playing that two's play in this bet game. You pair them together and let that be the play, two's play in this game. That means one is responding with something, yes? But what is one responding with? Yeah. So say, oops, let y be the play of two in G star, set x equals x0, x1 to be sigma star z plus y. Just put the z and y together and let's one respond to that. Okay, notice that L of x0 z is just L of z. Because sigma is coded by z, y is in L of z, y is two's play. So y is in L of z, z is in L of z, sigma is in L of z, so the entire play is in L of z. So these two things are equal, which means that bet game is the same. Okay, but now we then have
that one wins this one of G star. Right? Because one wins, sigma is a winning strategy in the parent game, but the parent game is saying that one has to win the game inside these local universes. But if once you're playing Z, that local universe doesn't change. That's the trick. Yeah. Okay, but I mean, the point of all of these is just that it is extremely difficult to cook up determined games. You can try. It's whatever you think is just not working. Yeah, and so the main thing I actually wanted to say, the way we got into this, is that sort of the phenomena has been that AD doesn't say much about objects of size greater than theta or even equal. You need, if you want to get interesting theory above with determinacy, then you kind of have to add that stuff. So if we want interesting theory, we need to kind of add that to AD. And it's unclear what it should be. It's unclear even what the goal should be. But you know, there's something like if this trunk model, for example, that has been recent, maybe chunk model satisfies AD. So chunk model will have stuff above theta if in non-trivial universes. And L-bar also is a chunk model, but it could be that there are countable sequences of ordinals which are not coded into the determinacy model. So you're adding them, and it could be that they satisfy the AD. So anyway, this is an ongoing. It's a theme in descriptive set theory, which is not very well understood. There is a paper by Steve, if you're interested. Long games. There he tries to isolate lots of hypotheses. Most of them are not known to be consistent, but at least we don't know that they're false. Yeah. Okay, I will stop. So next time we will do the effective version of coding lemma, and if there is time, I will give this proof, this Kekri-Soloway proof, more clear version of the proof, which was not supposed to be there, but anyway. Okay, guys. Ciao.
See you.
See you.